I welcome you all to the Spark Research YouTube channel. This is the another session for this course, Analog and Digital Communication. And here we are going to take the contents from the Unit 3. So this is the part first of this course. Here we are going to take the contents from this baseband and digital modulation techniques. And further in another part second, we will take the another part of this Unit 3, right? So before going ahead, let me tell you, you can join this, this channel for your GATE 2027 if you are preparing. And GATE 2027 is very important. Those who are going to complete the BTech in this year. And one of the important courses is your definitely analog and digital communication course. Okay, so here is the syllabus for our third unit. So primarily this if you'll see, then we are going to focus on the digital communication part, right? So we are about to start. So the before starting properly of this digital communication, before that we are going to talk about the pulse mode communication. So here we'll see the baseband modulation techniques, that is PEM, PWM, PPM, and then further we'll start the digital communication, digital modulation techniques, including the PCM, DPCM, and DM, right? So, so what is this pulse modulation waveform? So here you can see there are the three different types of this pulse modulation. That is, the actually in this type of the communication, this is the the analog signal. This one is your suppose massive signal, and these are your pulse. So we are going to stream the pulse for sending these message information. So our carrier is pulse train, and message is definitely this one, right? So how can we the vary the pulses? So if we are varying the amplitude of the pulse with respect to the message signal, that is called the pulse amplitude modulation technique, right? So that is PAM. Similarly, if we are going to vary the width, that is on the time axis of the pulse with respect to the message signal, then that is called pulse width modulation. Similarly, if we'll vary the position of the pulse according to the message signal, right? That is called PPM, that is pulse position modulation. So let's take in detail about these modulation techniques. So here is a pulse modulation, that is P pulse amplitude modulation. So here if you see, carrier is your pulse train, and this is the message signals. Message signals means that exactly we want to transmit, and here is the modulated signal. So this is pulse amplitude modulated signal. So now here if you will see, the pulse is same, means the frequency of the pulse is same, only the varying the amplitude. So here amplitude is fixed because this is carrier, and here amplitude is varying because of this message information. Okay, so here your message information will, like your pulse modulated mass information will vary after based on this message information, right? So by varying the amplitude of the pulse in proportion to the instantaneous values of the analog signal, right? So here mathematically you can write st, that is the sampled, that equal to summation of n of equal to minus infinity to infinity m of nts and p tf minus nts. So m and ts belongs to your message information and pulse train, that is pt, right? So here m and ts sampled message, pt is pulse train, and the ts is sampling. So key characteristic is that in this case your amplitude is fixed, and amplitude is going to vary with respect to the message signal, and remaining pulse width and pulse position is fixed, right? As for example, the application is earth net communication and ADC optical communication. These are the examples. Another type of modulation is your pulse width modulation. So here if you'll see, your pulse is this is the carrier pulse, and then this is the message information, and here see, here the width is varying, here width is less, and here width is comparatively very much less, right? So how will you decide the width is less, width should be high or less? That will be depending on the amplitude of the message. So depending on the message, so here amplitude is high, width is high. Here amplitude is very low, so width is very low, right? So similarly, you can decide your width of your pulse train. That is called the pulse width modulation. So here the pulse, the amplitude will be fixed and position will be fixed and width will vary. So advantage is that better noise immunity compared to the PAM and application motor speed control, especially in BLDC, right? So similarly, we'll have the PPM, that is pulse position modulation. Right here, you can see the last one that is belongs to the PPM. So position of your pulse train here. See the here the pulse train, it should be here, but it's left shifted. Similarly, somewhere if it is right shifted. So position of your pulse is shifting according to the message information. So that is called the pulse position modulation. So by varying the position of the pulses in proportion to the instantaneous values of the analog signal, right? So advantage is high immunity and application is optical communication radio wave system. Here is the summary. So message signal is here. Here PAM is there. PAM means this pulse train, right? Pulse train. Only check the pulse train. And here the PWM is here and PPM is here, right? I hope you got it. Okay. So now we'll start the digital modulation. So before going to start the digital modulations, some fundamental techniques are there. First fundamental tool is that sampling and then quantization. So sampling is your like how will you sample your analog message on the x-axis, means on the time axis. So sampling rate must be the equal to or greater than twice of highest frequency, that is f of m or b of m, right? So that is called Nyquist rate. So like first you are going to divide your message signal on the x-axis, that is on the time. So that is called the sampling, and the rate of sampling is must be greater than twice of. Otherwise, if sampling rate is lesser, then in that case, aliasing will occur. Aliasing means distorted message, right? So we'll see in detail about it. So according to your sampling theorem, like it's a sample taken uniformly at rate, rate is must be greater than twice of b. In other words, minimum sampling frequency is fs equal to twice of b, right? Why is it so? So here g of t is there, and that will be the g of t and del of ts. That is how will you sample it. So this is the sampling, and this is the message information that you are exactly going to sample. So suppose this is your message information and this is your impulse train. Pulse train is here. And so in the frequency domain, this is in the time domain, and in the frequency domain, you can check it here. It have the bandwidth of twice by v, and the minus b2 minus plus b. So finally, the bandwidth will be twice of b. So through the ideal low pass filter, if you pass this, then the minimum bandwidth, that is sampling rate, will be twice of b, right? So if it is, if you want to recover, and if you will have the bandwidth lesser than this, that is twice of b, in that case what will happen? The sampling interval will be the less than one of the twice of b, and so this is the Nyquist interval. So Nyquist rate is your greater than twice of b, that is sampling frequency, and the time interval corresponding to that sampling the frequency is called the Nyquist interval. So here is your PCM now. So PCM is your pulse code modulation. So this is, suppose blue color is your message signal, and red color, this red, yellow color or red color, whatever you can say. This is showing the PCM output, right? So here, if you'll see, here not only we are sampling on the x-axis, but also we are taking the approximate value on the y-axis, right? At every moment of time, right? So that is called the quantization. So sampling on the x-axis and quantizing on the y-axis, that results into the PCM, that is pulse code modulation, right? So let's see how to do in the better mode. So first of all, how will you reconstruct the message? So using the interpolation formula, we can, the process of reconstructing a continuous time signal GT from its sample is also known as the interpolation, right? So how we'll do that? So the function here, you can see the reconstruction interpolation filter transfer function is h of omega is equal to ts rectangular of omega by 4 pi d. So here, like we have the sample signal in the rectangular function, means whenever we'll have the rectangular function corresponding to that, we'll have the in the time domain, that will be the sinc function, means the inverse Fourier transform of rectangular function, automatically it will give you the sync function. And now if you will interpolate either interpolation, then definitely you will get your proper message. So here suppose if you are if you are sampling, these are the sampling instance. So corresponding to the sampling, you will have the multiple rectangular, and if you will the get one sync function with the one rectangle, so similarly you will get the multiple sync functions due to these multiple rectangle functions. So if you will add all these sync function like this that is called interpolations, then finally you will get the sinusoidal wave, that is the your message wave. So this is the technique, right? Yeah. So just the key points is that the rectangular function, this is the frequency domain, that is Ts, and rectangular function of omega by 4 pi b, and so pi b and twice pi b, so 4 pi b bandwidth, and corresponding to this in time domain you can write the sync function. So both are same only, this is in frequency domain and this is in the time domain. Okay. And to issue of aliasing, there is another fundamental practical difficulty in reconstructing a signal from its sample, that if your the your sampling frequency is the lesser than that twice of b, in that case what will happen, it will have the aliasing, right? You may not able to reconstruct the original signal. So that means if interval is less, like lesser than the Nyquist interval, that will then only it will be the problem. So question is that how can we resolve this problem? So we can use the anti-aliasing filter that can remove these reasons, right? These entire bandwidth. So that definitely you will lost some information, but at least you can reconstruct the message. So you can use this. Okay. So sampling, that is sample the data on the x-axis. Quantization means quantizing the data on the y-axis, and finally will leads to the PCM. Okay, so here is the final PCM. PCM is the most useful and widely used of all the pulse modulation mentioned. Basically, PCM is the method of converting the analog signal to the digital, right? So before that, whatever we have discussed, the like PM, PWM, they that are not the example of digital communication. This is the first or basic digital communication technique, right? So here you can see now the signals are pure in the digital format. Now whatever you have got the final value after the PCM, now you can encode that message either like in the digital using the 1 bit, 2 bits. It's depending on your bits, right? So now if you are encoding that message, you will get the proper pulse train, right? So that is the example of the digital modulation technique, right? So this is the PCM, pulse code modulation. So here if you'll see how can we find out the quantization noise and the quantization. So here you can the if you are quantizing your max y-axis, that is amplitude, means you are approximating the values of the y-axis as well. So what will be the the level of your interval, that is the step size. So you can find out that is del v equal to the suppose del v is your step size. So you can find out like MP, suppose MP is the peak voltage, so peak to peak, that is twice of MP, and divided by L is the length of your the L is the one of the numbers, that is L will be the 2 to the power n is the number of bits, right? So in that manner you can find out the del of B. So del of B is nothing, that will be equal to your twice of MP divided by L. Clear? Now we will try to find out the quantization error, since we are approximating the values of the amplitudes on the y-axis. So definitely if you are sending the some information instead of the some amplitude, so it will have the some deviation, that is called the quantization error. So how much will it be? So suppose this is the MT, that is M, KTS and sync functions. Why sync function? Because in the time domain your rectangular function will becomes the sync function. So take the convolution here for MTS actually this is the M bar TS, that is quantized one. So take the difference, that is QT is equal to the quantized one and minus analog. So digital one and minus analog. So that will be the error, right? So QT you can write the difference and then the multiply by the sync function. Okay. So this is nothing, this is the QKTS and this is the sync function, and further you can get the average value. So this is the quantized error value, but let's get the average of the error, right? So integrate it over minus t by t2 q square t2, this one. Now just put the value and integrate it. You will get the q square is equal to limit t tends to infinity 1 by twice bt and q square qbt. Further, if you will solve and put the value of del v, that is twice of mp by l, that is the limitation, and you will get the value del v square divided by 12. So final value is your m square p by 3l square. So this is the q square, that is error, that is noise, right? So noise you can write m square p divided by 3l square. So that is also called the quantization error, right? So here signal power is your nothing m square t, and noise power already we got. So SNR, that is signal to noise ratio, is signal divided by noise. So this will be the signal to noise ratio. For SNR for n bit PCM, you can also find SNR is equal to, since here we already got, that is 3 by 2, you can write, and L square, right? So here now if you will put L is a number of the quantization level, that is L is equal to 2 to the power 9. Now if you will put the value, then you will get SNR in dV, that is equal to 10 log 10 and 3 by 2 L square. So value will be SNR will be equal to 6.02 and into n plus 1.76 dB. So directly you can get the value of SNR into the dB for PCM using this formula if you know the number of bits, right? So one of the important results you can remember. And now we will talk about this is the quantization what we discussed, that was uniform. Sometimes you can do it non-uniformly, right? Non-uniformly means like here, if whatever the quantization level you kept 0 to 1, 1 to 2, 2 to 3, 3 to 4, that is uniform. Sometimes you may keep it non-uniform, means if your functions, your signal is varying rapidly to minimum to maximum or something like that. In that case, you can it's not necessary that the interval you choose 0 to 1, 1 to 2, 1 to 3. Sometimes you can vary it. That is the non-uniform, right? So the two types of the non-uniform techniques we are using, that is one is A law, one is mu law. So according to mu law, y will be your 1 by ln 1 plus mu ln 1 plus mu m divided by mp. M by mp is in between 0 to 1. Similarly, A law, you can check it here. That is how you can write the value of y, right? Now we are going to talk about the DPCM. So DPCM is nothing, difference of PCM, right? So here, like instead of sending the bit, same bit, like in the PCM we are sending 1, 2, 3, 4 and respectively. Here we will send the difference, first bit, and then difference in between first to second bit, difference in between second to third, third to fourth, like that. And why is it so? In order to save the number of bits. So that is our objective, because if you are using the more number of bits to send the same information, ultimately bandwidth will be very high, right? So we want to reduce the bandwidth, means we want to use the less bandwidth, right? So that is why this the DPCM is important one. So DPCM stands for your differential pulse code modulation, that is DPCM. So in DPCM we transmit not the present value, that is mk, but dk. Dk is the what? Difference between mk and its predicted value, right? So at the receiver we generate mk, that is from past sample value, to generate the received dk is added to the generate. This is however one difficult scheme. So here input is there and delay, and then you can send the a1 and again delay, and you can send the a2, and you can keep on delaying, and then you can keep on sending the information, right? So mk is a1, mk1 minus 1 plus a2 and k minus 2. So keep on delaying, right? And once you will keep on delaying, you will get the m of k. So DPCM transmitter receiver here is there, and you can find the noise also. So here dq noise is equal to the dk plus q of k, and so the output predicted, that is mk m dash k, you can get it from here. And here is a predictor which will predict here. So the mk is there, quantizer is there, and once you can take the difference, and you know, the whatever the difference you are sending, you can just detect, and you can keep on adding into the previous signal. So no need to send the all the information. You can just add the one difference, and then you can send that particular information based on the prediction, right? So here instead of sending the entire mk, you are just sending the difference. So you are in loop, so you will keep on sending the difference, right? As for example, you can send the information, first time you can send the information 0, and then second time you can send the information 1, and third time even if your amplitude is 3, still you need to send the only message 1 only, right? Because the difference 3 minus 2 is 1. Similarly, fourth time also you will send 1 if it is the signal is 1 2 3 4, like that. So delta modulation is the one of the special case, right, of your DPCM. Not like there is no much more difference. So here also we are going to send the difference only information. So like delta modulation. So here how can we send? So here like we'll compare the information from the previous message, and then we will send the difference in between, and then finally we can decode the encode the information and will send right to the channel. So that is the final message information corresponding to this message. Okay, so delta modulation here, the simple correction used in DPCM is further exploited in the delta modulation by oversampling and the baseband signals. So this increases the correlation between the adjacent sample, which results in a small predictor error that can be encoded using the only one bit, that is L is equal to 2. Thus DM is basically one bit DPCM, right? And that is DPCM that uses only two levels for quantization of MK minus MQK in comparison to PCM and DPCM. The in delta modulation, very simple and inexpensive method to analog to digital converter. So one bit code word is in the digital delta modulation makes word framing necessary at the transmitter and receiver. This strategy allows us to few bits per second, right? So here you can find out. So the major thing is that now here comparator is there and sampler is there and then integrator. So based on the previous information it can integrate and then you can send the information using this. But problem again here, the problem will be like if you are sending using this delta modulation, so if like if your message signals will stagnate at certain level, then you are keep on going up and down, up and down, up and down, right? So this noise will occur, so that is called the granular noise. And again, if your message information is the decreasing or increasing faster than the rate of the your delta size, then again this will be the another type of problem, that is called slope overload distortion, right? So these two different types of problems will occur in the delta modulation. So granular noise, because now if you want to fix these problems, so granular noise you can fix like if step size is very less you can fix. But again, if your step size is very less, in that case slope over load distortion will be very high. And if you will keep higher value of your delta size, step size, in that case slope overload noise will be less, but granular noise will be high, right? So we have to optimize. So how can we solve this? So the challenges you can solve like using the delta adaptive delta modulation, where the step size will keep on changing with respect to the message information. If message information is stagnant, in that case delta will be lesser, and if it is changing quickly, delta will be higher. So that is the this is one of the solutions. In that case you can find out the SNR, that is equal to A square by Q, and you can remember this SNR is equal to 5.34 beta T by B into MS square T divided by MP square. Now, comparison with the PCM, the SNR in DM varies as power of the BT by B. So here you can see the comparison of these PCM mu is equal to 0 and PCM mu is equal to 100, means the mu law based, and the delta modulation for the double integration and delta modulation for single modulation, right? So conclusion is that DiEM can outperform the PCM at low SNR, and but it is inferior to the PCM in high SNR case. One of the advantages of DiEM is its simplicity, which also makes it less expensive. However, the cost of the digital components, including A by D, that is analog to digital converter, is coming down to the points that cost advantage of DiEM becomes significant. Here is the overall, so you can check it here. Here is the adaptive case. You can the vary the size of the delta model, the size of the step size. That is why you can reduce the slope overload here, and here you can also reduce the granular noise. So this is the one of the best technique to use the analog to digital converter. And after the converting into this step size, finally you can encode the message, and then finally you'll have the digital information. So this is the way to convert, right? So these are the techniques to convert your message from analog to digital. Okay, so that's all. Thank you to join the sessions. If you have any doubts, please drop a comment. Thank you.